So now I would like to take this precious opportunity to welcome Professor Shi to our general chair to give the introduction for the keynote.
Okay. Thank you, everyone, and thank you, Borji. Now I will start our opening keynote. This is our great honor to have Professor Tei-Wei to give us opening keynote here. Professor Guo has been known in this community for a long time, but I see many new faces, so I will take a very short time to give a short introduction to for Professor Guo. Professor Guo received his BS degree from this department, and have his master and a PhD degree from UT Austin in 1990 and 1994. It's almost 30 years ago. Okay. He is currently a distinguished professor in this department, but before August this year, he actually served as the chair professor of information engineering in the City University of Hong Kong, and he also served as advisor to president and the dean of College of Engineering in the City University of Hong Kong. Before he took the temporary leave to City University of Hong Kong, he also served as the interim president of this university, okay, from 2017 to 2019. Okay, and Professor Guo actually received numbers of awards. I cannot list all of them because that will take all the time for his keynote speech. But I just want to highlight that he received both the ACM and the I3 Point Fellow. Only very few people in the world have this honor. Okay. And he also received also a fellow of U.S. Academy of Inventor, and recently he also received an award from the German Humboldt Award. Okay. So without further delay, please join me to welcome Professor Tei-Wei.
Thank you. Okay, thank you, Professor Shi. Okay, and it's actually my great honor to come back to National Taiwan University after I go out for more than 3 years. Okay, in fact, it's the first physical conference I attended in the past 3 years. Okay, and I'm so happy that that's RTCSA and NVMSA. Okay, so today I'd like to talk about computing. Okay, it's over 70 years. Okay, since we have the first computer. People always think the computer should be the way, the style we saw today. Okay, in fact, people have a lot of thinking. What should be the coming or future computer? Okay, so today I'd like to take this opportunity to talk about computing, especially the designs. Okay, So today I'm going to talk about memory-centric design. Okay, in the past we have been CPU-centric designs. Okay, then I'm going to talk about how to close the gaps between memory and also storage. Then I'm going to talk about in-memory computing, and then conclude my talk. Okay. So as I just mentioned, that it has been over 70 years since we have the von Neumann architectures. And we used to build computer in the way we like. Okay. And it's also over 50 years since we saw the Moore's law. Okay. We double the number of transistors every 2 years. Okay. It's been going on for decades. Okay. Even though people now wonder whether we can go on forever. Okay. Then it's been over 30 years since we have triple W. They actually changed the way people share data globally. Then 15 years ago, Amazon and IBM start to bring a new way of computing platform to the world. So we know that there's cloud computing. So since then, we see a lot of interesting things happening, okay, such as the growth of human and machine generated data. The growth rate of those data, like human data or sensor data, they all grow at a rate or pace much faster than the traditional business data. And with the exponential data growth in the past and coming years, okay, we also see the synergy of AI and big data. There are lots of business opportunities out there. So people always think that if we can build a huge computer, huge data center, we can process all the data in the world. But in fact, it's not. Because if you look at the reality, maybe, I mean, based on some of the study, maybe more than 70% of data will never reach the data center. It must be processed before it reaches the data center. Otherwise, it cannot support all the application we have today. So people might wonder what kind of computer we should build. Okay. So it may not be the world we enjoy in the past decades. Okay. So, well, before we go into detail, let's look back in the history. What's been happening in the past years? Well, when we have a lot of computing needs, people think about multiple cores. Okay, we have so many CPU to process our data. Okay, then if you consider performance, energy consumptions, and other factors, people think about, oh, we should have heterogeneous cores. Okay, of course, with heterogeneous cores, you can actually optimize the performance and costs. But somehow you want to push the performance and cost further. So people start to have like hardware threads. Of course, they are not good enough. So people invent FPGA, GPU, ASIC chips, okay, to solve their computing problems. Okay. But as you can see that it actually doesn't solve our problems. Okay. Because, well, you see that for computer, there are many different components inside. We cannot just focus on CPU. For example, you see the big performance gap between the storage and CPU. Okay, not to mention the gap between memory and your CPU. So that's why, well, people think about the bottlenecks. Okay, how should we scale up our system so that they can meet the future needs? For example, if you look at the deep learning, okay, I take some example from past reports. Okay, you see the growth, the bandwidth needs for deep learning algorithms. Okay, in fact, if you want to keep up with all the data that you are collecting and go with the application that you need, you will need an exponential growth of the memory bandwidth so that you can keep up with what you need and consider the GPU and CPU power you have. So that's why people start to invent high bandwidth memory bus. Okay, for example, high bandwidth memory. Okay, so that we can keep up with the need to move data in the system. Because all the machine learning algorithms require high memory bandwidth. So people have to think about, can the current AI solution be scaled up with what we need in the future? Okay, so people might think, well, if that's a problem, okay, so where are the bottlenecks in the new era of computing? Of course, if you have all the data, people tend to think that I have all the data in the data center. They are in the cloud. Then, consider data center or the servers in your department, for example. You have to think about how to download the data from the cloud to your servers. Okay, think about the amount of data you need. Okay, that's huge amount, right? It's hard to imagine. Okay, well, if you think about it that way, well, think about your storage. Even though we have solid state drive right now, they can be very fast. The access time can go down to like millisecond or microsecond. Okay, 10 to the -6 second. Okay, so if you think it in that way, if you have zettabyte of data, how much time you need to download your data? It takes days. Okay, don't think about the application or the enjoyment you want to have for your application. Okay, so it's not practical for you to download your data from the cloud to your server for your computing. Even though you can download your data from your cloud to your storage of your servers, you don't even have time to upload your data from your storage to main memory. Even though your memory is fast, like nanosecond, 10 to the -9, okay, seconds. You have zettabytes of data. How much time you take to upload your data? Well, days, okay. Well, then think about the challenge. When you have data all in the memory, how much time you need to move your data from your memory to your GPU? Even your GPU is extremely fast. Well, it might take days. Okay. So with that in mind, you will think, well, maybe we have a lot of bottlenecks in computing. With all the beautiful invention of deep learning algorithm, they may not be feasible for our future application. Even though we collect so much data, we don't even have time to process them. Okay, we cannot meet the needs for user. For example, when people are doing auto driving, you tell him, sorry, okay, your data have been uploaded until tomorrow. Okay, so how can you do auto driving, right? So then you probably start to, believe that most of data probably could not arrive at the data center on time for your applications. Okay, so it's not a problem for your processing in the data centers or on the edge. You just don't have time, okay, to process that. Okay. So for computing, you have to go back to the original design. Okay, we have volume architecture. Okay, volume architecture tells us that you have data. Those data have to be stored in storage. Before the computing, you have to move the data and programs to the memory. When you do the computing, you have machine cycle. You have to load your instruction to the CPU or GPU. Okay, whatever way you like kernel, you upload a batch of, a bunch of codes. Okay, you have to do it in that way. You have to move data into a GPU and process and move it back and move it in and move it back. Okay, you have so much data. Okay, so that's actually the artificial limitation for computing because we use the volume architecture. So people have to think, well, maybe something wrong about volume architecture. We use that for decades, but for the future, they may not be so useful as we think. Okay, so what should we do for that? Well, you have more and more data. Okay, and your computing component go faster and faster. Okay, but your storage does not go in that way. It becomes fatter and fatter. Okay, it bigger and bigger. Okay, it doesn't go with the speed or performance you like for your computing components. So the gap become wider and wider. Okay, even though you can collect so much data, but so what? You cannot compute. Okay, so the performance gap between CPU and storage goes wider. And think about this as main memory, not just storage. That also go wider and wider. Okay, so if we go in that way, then think in this way. We have so much data, it goes exponentially. Okay, there are some data from different companies. For example, Facebook and others. You see, the data being used for those systems actually need a lot of DRAM. They go up like exponential. So all the data, the amount of data go exponential. Okay, and the needs for storage and memory also go exponential, but they do not go fast. Okay, and you have CPU, GPU, they go exponentially fast. Okay, then what can you do? So in some way, we have to break the architecture. Okay, redesign our computer. That's why we should think about it. Okay, for the future computing, it may no longer be CPU centric. You may have to think about data. So put it this way, they may be considered as memory centric for your designs. Okay, and so the center of universe probably change. Okay, it shift. Okay, from the way we think in the past decades to the new center, like data. That's the center. Without data, you don't have intelligence. Without data, you don't have service. Then what can we do? Well, today I'd like to talk about two past work with my student and former students. Okay. Well, I'd like to talk about how to close the gap between main memory and storage. Then we talk about new paradigm in computing, in memory computing. We talk about the challenges and what should we do for the in-memory computing. Okay, well, for the non-volatile memory, we see a very successful stories in the past 2 decades. Okay, well, we see solid-state drive. Okay, we are going to have an expert tomorrow to talk about solid-state drive. But before we do that, I'd like to give you some idea, okay? Flash memory is one kind of non-volatile memory, okay? That was invented in late 1980s. After that, well, there are different kinds of memory being invented. Okay? I mean, if you look at the entire trend, you will see all the non-volatile memory chips, they become cheaper and cheaper. They have a higher density, larger and larger capacity. Actually, the growth rate of their capacity is like you double it every 18 months, even faster than Moore's law. Okay, but at the same time, you have worse and worse performance, worse and worse reliability, and shorter lifetime. Well, because of market needs, you need to have a good and compatible product. People drive the cost. But anyway, there are different products being invented in the market. Okay, so there are storage class memory, and they try to replace DRAMs. Okay, so before 2012, people look at two-dimensional chips. Then after that, people have three-dimensional chips. So they boost the capacity and the cost and reduce the cost. Okay, and as a computer scientist, we always look at the hardware architecture and system architecture. We try to compare them. Okay, for example, we compare them from chip, storage, file system module, all the way to application. And at the other side, you see different memory hierarchy from your storage memory all the way to SRAM. Okay, so if you look at your software layers and also the hardware architecture, you will notice that the gaps between memory and computing storage are closer than ever. Okay, for example, before we have solid state drive, the performance of hard drive is the latency is about millisecond, right? 10 to the minus 3 seconds. Then you have solid state drive. So the performance become like microsecond scale. Okay. So actually the performance increased by 1,000 times. Okay. But your memory performance stay at narrow second. See, so the gap between storage and memory actually shrink. Okay. It's actually between the millisecond, nanosecond to microsecond to millisecond. Okay. Actually keep shrinking. Okay. Some of the non-volatile memory actually have performance so close to DRAM. Okay. So, and also the capacity of those memory actually grow at a pace faster than Moore's law. Okay. And the boundary between those hardware software become so blurred. Then one thing people might think, how to close the gap between main memory and storage. One way to do it is to unify them. Okay. So your storage memory storage. Okay. It's not so strange. Okay. It's like you have a hard drive. When you have hard drive, you logically partition it into several drives. Okay. So you call it drive C, drive D, drive E. Okay. And you can do it in the same way. You got the memory chip. You partition it as the memory and storage. That's it. Okay. And use the memory part as a memory, storage part as your storage device. Okay. So people invent different kinds of hardware to do that. Okay. For example, NVD. This kind of product actually has DRAM and also flash memory. They put in the same module. Okay. And put in the DIMM slot. Okay, and use that as a main memory. Okay, but see, you have in the module you have DRAM and also slower memory, NAND flash. That's actually been used for solid state drive for years. Okay, so but you use the entire NVD as a memory module. So what will happen? What happens is this: when you replace the DRAM with this kind of module, you might have some gray memory wall. So what is gray memory wall? That is when the computer system somehow touch the slow memory, your system will probably hang there because it's slower than DRAM. Okay, but well, you say that, well, that's a problem. Yes, that's a problem. Okay, otherwise people can just go here and buy this product, right? But in the past, people try to use DRAM, but DRAM is more expensive. Not just more expensive. When you have a lot of DRAM, they're actually very energy hungry. Okay. It also generates a lot of heat. Okay. But anyway, if you consider this kind of module, hybrid memory module, So if you touch the DRAM, faster memory, it's go very fast. But if you somehow touch here, then you go down, performance go down. For system designer, you have to solve the issue. Then the problem is, well, if you want to have this kind of module, how do you change your or modify your operating system design so that you can enjoy the huge DRAM? Okay, that's actually come from NVD. Okay, at a very, very low price. Okay, so you can enjoy like terabyte your main memory, but with a very close, very low cost, close to your solid state drive. Okay, that's what people want to do. Okay, so if you have great memory wall, okay, with some power module you have like NVD, okay, then you will think about the entire system design. When system handler because you touch the old memory, what operating system should do? Okay, and also what can you do to optimize the performance? Okay. So if you think deeper in that direction, you will see that, well, we have to consider the information processed by, controlled or managed by the operating system. And all the information that actually known to the hybrid memory module. You have to close the gap, okay? Because they have different idea, okay? For operating system, they know everything, including the memory usage and also the status of the running process. But for storage or memory module, they don't know. They are just a dumb, very dumb memory module. So somehow you have to close the gap, okay? And somehow push some information down to the memory module and use that very smartly. Otherwise, you are going to complicate the design of NVD, okay? So the problem is how to process access information over the virtual memory space and improve the data relocation effectiveness in using a hybrid memory module. But I won't go into detail, okay? Let me use the following example to tell you some ideas, okay? First, let's look at some observations, okay? When you look at process, okay, I know most of you already take operating system courses, okay? I assume that you know virtual memory, okay? When process are running, they see their virtual memory, okay? So they imagine their memory is from address 0 to down to a very large number, okay? So anyway, when they are running, they actually show some strong spatial locality, okay? We access some instruction or data, you actually will also access some addresses, close to those addresses, okay? And in fact, when you run different algorithms, okay, you will see some interesting pattern, okay? And I show you some pattern here. I show you some access pattern here, okay? And that's actually some specs, okay, like TensorFlow, Caffe, Blender, etc., okay, etc., okay? And if you look at the access pattern, okay, the x-axis is actually those benchmarks, okay? The y-axis is actually the percentage of data access, okay? You probably can see that we have two kinds of access pattern. This is non-continuous access. The black bar is actually continuous access. You can see a high percentage of continuous access. Okay, that means when you are executing your program, there are a lot of, computing component actually show spatial locality. They are continuous pattern. When they access some address, they probably access the following address or some address just before that. Okay, so if we call the access pattern that you keep accessing those addresses following the previous access, that's a forward continuous. Okay, and sometimes you'll see some backward continuous in certain image processing application algorithms. Okay, so if you look at the other figure, you'll see that if you look at TensorFlow, Caffe, and Blender, you see they have lot of, for all the continuous access, you have a lot of forward continuous access pattern, and also a lot of backward continuous access pattern. Okay, so how can you utilize the information and notify your MPD to do relocation for you? If you can do that, you can actually speed up the process. Okay, so that's actually what I'm talking about. The whole design is this. I won't go into detail. I just want to show you the idea. Okay, the idea is this. Okay, well, you have CPU that may actually issue some request. Okay, to your NVD module. Okay, but somehow if you keep the NVD module, and somehow if you are unlucky, you hit the slow memory, your NVD module will probably slow down and hang there. Okay, so if it slow down and hang there, and your CPU notice that, then you know, oh, it's hanging. Okay, then we go back and look at your access pattern and see and do some analysis. Is it backward or forward continuous accessing? If it's forward backward accessing a continuous access pattern, you can use the semantic aware strategy to think about it, whether it's continuous forward, continuous backward. If you know what it is, then you send some information to the NVD. Then you tell them, okay, I'm going to mark some page. You start doing some page relocation. Okay, so it's more or less like prefetching in your operating system. So your NVD is so dumb, it doesn't know anything. So you receive some command, okay, for prefetching. Then you start prefetching. Okay, so that's the only thing the NVD controller should do. Okay, so anyway. And at the same time, for your CPU, your operating system scheduler, you need to be aware of the store. Okay, then you do some rescheduling. That's the only thing you need to do. Okay, let me use this example to show you a little bit. That's don't go into detail. Okay, so see, this is the diagram you have. We learned that in our operating system courses. Okay, so when we have some process being dispatched and running, okay, if you somehow hit slow memory, okay, you have long storing, okay, then we hope that the NVD controller can have a signal back to your CPU, long storing, okay, then you can move the process into exception state, okay, then the exception state, you do a very quick analysis, okay, and see whether you have some access pattern to consider. If you have, then you send message page marking to NVD. Ask the NVD module to do relocation. Okay, that's it. Okay, then for your operating system, you can keep doing that or send the process to waiting because you have some relocation. So you should reschedule other process. Okay, so you don't need to have your operating system handle. Okay, so that's the only thing you need to do. Okay, so of course, that's a design we consider. Okay, I don't go through the detail here because I'm a little bit slow. Okay, so anyway, there are some simple data structure you can maintain. Okay, for example, you maintain some access pattern. We call the data structure like page on page unit. It's actually is a fixed length continuous chunk in the virtual memory. Okay, so you want to manage that in a coarse grain. Okay, so whenever you have some access, you put the POP into some data structure. Okay, remember that when your NVD slow down because you hit some slow memory module, and you have some signal sent back to your CPU, then CPU go back and look at the POP data structure. And quickly look at the history and see whether we have continuous or backward or forward continuous access pattern. If they see that, then you set page marking down to the NVD. Then you do rescheduling. Okay, that other process running. Okay, that other process wrong. Okay, so that's a basic idea. So the whole idea is very simple. Okay, when you have some access, you see whether it's continuous, you start marking. Okay, if it's not continuous, it's actually go with some spatial locality, then you go to some kind of LRU to marking. Okay, so very simple algorithm. Okay, and that's a data structure. I won't go into detail. Look at the performance. Okay, we try different benchmark. Okay, we do simulation over a 16-way set associate a megabyte CPU cache. Okay, and actually we have the memory trace for all the benchmarks application extracted from Intel Pin and Belgrid. Okay, so there are different benchmarks. Okay, from for example spec CPU 2006 and 2017. Okay, and some of the specs actually have forward and backward continuous access pattern. That's a percentage. For example, TensorFlow you have 21% of data access being non-continuous. Okay. For forward, you have 26% of forward continuous access pattern. And 53% of the access pattern belonging to backward continuous access pattern. Okay. And you try to mix them in some way to see what happened for the evaluation. Okay. So, well, then let's look at what happened. Okay. Well, the x-axis is actually the applications. Okay. And you compare the performance with some LRU-based relocation algorithm. And the other one is the ideal case, whole memory, whole DRAM. Everything is DRAM. Okay. You don't consider slow memory. Okay. You put everything on DRAM. That's ideal case. Okay. But that's expensive. Okay. So the second one, actually, our algorithm I just showed you with forward prefetching consideration. And the second one is forward and backward prefetching. Okay. You can tell that, well, when you have consider some benchmark that has forward and backward prefetching needs, then you can see that we can actually, sorry, this one, okay. So you can see that actually a difference between the second and third one, okay. If you consider backward access pattern, you actually can have the very good average performance close to DRAM cases, in those cases, okay. Okay, so, and the other one is actually a mixture of data pattern. Okay, the previous figure actually for each individual benchmark. Okay, for those mixed pattern, you will also see the similar things. Okay, for example, look at this one: mix one, mix two, mix three. Mix one, mix two, mix three actually have a lot of mixture of some benchmark with forward and backward access pattern. So you see the difference between the second and third one. Okay. So actually, when you consider backward access pattern and do prefetching, you actually can boost the performance a lot. Okay. So for the trade-off, for the best performance, okay, for the evaluation of the trade-off for best performance, we actually set the DRAM size to around 40% of size of memory footprint, because after analysis, we can see that this kind of DRAM can actually capture most of the working set for those benchmarks. Okay, so we want to see how close we can do. I mean, compared to ideal cases. Okay, well, let's look at this one. Okay, you can see that consider backward and forward verification, backward access pattern. The last bar is actually for whole DRAM. Okay, you see the performances can be so close to the ideal case. Okay, okay, even though some are a little bit gap, but they are very good. Okay, okay, so the previous talk about how to close the gap between memory and storage. Okay, we proposed a storeware process scheduling. Okay, so that you can know that the slowdown of your data access or DRAM access, and try to close the gap. Okay, and try to pass the information from operating system to your MVD module. Okay, so with that simple design, you actually can have your performance very close to a system with entirely DRAM. Okay, okay. I'm going to go to the second part. I take too much time to talk about that. Okay, so the idea about how to close the gap between memory and storage, we actually still stay with von Neumann architecture. As I just mentioned that, if we want to look into the future, we are going to go to some point that you can no longer do that because there are so many data. For this kind of, for the talk, the first part of my talk, that actually solves some problem for I/O bottleneck. Okay, because when you have unify the memory and storage, you actually reduce the data movement between storage and memory because they are all on the same components. Okay, and you have huge memory. You actually virtually swallow everything into your main memory. You don't need to load your data again from storage because they are all in the memory, a huge memory. Okay, but well, not only solve the problem partially. Okay, as I just mentioned, even though you have all the data in memory, you still don't have time to move it into CPU or GPU or ASIC chip for computing. Okay, so let's look at the in-memory computing. So why look at in-memory computing? As I just mentioned, okay, think about the computing we have, okay, today, such as deep learning. Okay, this is a typical deep learning algorithm. Okay, you have so much data to be pushed into the neural network. Okay, so for every edge here, you have a multiplication and summation. Okay, so see you have like millions of edges in your machine learning or neural network algorithm. Okay, so we actually have huge amounts of data. Okay, millions of weights. Okay, millions of parameters, and billions of data. You have to push it all the way through the neural network. Okay, so you are going to have a huge data volume, not just your storage, okay, your input, but also your weights and parameters. You have to process them very fast. But see, you have millions of edge here. Okay, you probably don't have billions of computers. Okay, or computing units. Okay, so you probably need huge parallelism. So in fact, as I just mentioned in the first part of my presentation, that's actually von Neumann architecture restriction. Okay. Well, so for all the computations you do for our von Neumann architecture, you have to load every instruction, decode it, and load your data, and run the machine cycle, then load the next one, and load the data, load the instruction, decode it, and run it, set data, and do it one by one. Okay. Even though you have GPU, you have to do, I mean, there are millions of edges, you have to do it. So you need huge parallelism. Okay. And well, it's okay for computing because you have so many computing nodes. But the problem is you don't have time to move data. Okay. So before you do computing, you have to move data in. After computing, you have to move data out. Then move data in again. Okay. There's so much data. Okay. So can we combine the memory and computing? It's like your neuron. Okay. It's like your neuron. Then every unit is a computing unit and also storage unit. So think about it this way. Okay. Every node is a neuron. When you push data in, they actually flow all data from the front end all the way to the back end. Okay. So it's no longer machine cycles. Okay. It's more like a natural process in your processing in your brain. Okay. So that's actually memory computing I want to talk about. Because the reason for people to think about in-memory computing is because the hardware performance actually bottlenecked by the limited bandwidth to shuffle data between components. Okay. So can we remove the data transfer entirely? If you want to do that, think in this way. You have a neural network here, model here, or deep learning algorithm, and you have machine here. Can we map the entire model into the machine or your memory chips? Okay. Then every weight here then become the resistor value here. Okay. When you put some input here, it's equivalent to you put some voltage on the wall line. Then the current will go through the cells. Okay. Then you connect all the output together. It's more like a summation here. Okay. So what I'm saying is that, well, you have your machine, you have your algorithm, you combine them. It's like your brain, right? If you are learning, you actually adjust your weights and parameters. You keep learning and keep adjusting your weights. If you want to think about whether it's a dog or cat, you have input, then it's like you put voltage here, input flow, I mean, all the way through your neurons, and you have output. Oh, it's a dog. Okay. It's more like that. Okay. So if you combine them together, what's the challenge? Well, the first challenge is scalability. If you can build this kind of memory chips, okay, can we build billions of chips? I mean, and do the neural network computing? Okay, scalability, that's the first challenge. Secondly, if you put them together, think about you have billions of neurons or billions of CMOS, components inside your chips. You have to control latency. When you have input, you have to have the output instantly. Okay, latency should be very short. Okay, and it should be endurable because some of the memory actually will be worn out if you write it too many times. Okay, because you keep updating, the material will be broken. Okay, for some of the memory, when you write it, take more memory, take more energy. You have to control the write energy. Okay, but if you do it the right way, you actually can save so much energy because this kind of structure is different from the neural architecture. It's actually more like a brain. Okay, that's why when you have your breakfast, dinner, your lunch, and you can working, you can thinking, you can write your paper, right? But if you do our deep learning algorithm over our current computer, it's more like simulation. Okay, simulation of your deep learning algorithm. Okay, it's like you have a computer today. You are going to do something that's actually not designed for this kind of computer. So you have to have native design. Otherwise, you cannot solve the problem. Okay, there are many studies people have done before. If you do it this way, you can actually reduce the energy consumption by several magnitude, scale of magnitude. Okay, maybe 1,000 times less or million times less in performance energy consumption. Okay, anyway, so if we do it this way, we have to think about application co-designs. There are many kinds of applications you might have in mind. For example, speech recognition, object detection. The problem is that you have to map the neural network model over your in-memory computing device for computation. Okay, so what you are doing is, what are you doing will be like this: have the algorithm and map it on the chip. Okay, and have all the ways being recorded as a resistance value. Okay, then that's it. Then the problem is, how can we reduce the data volume? For example, how do you update every cell? Because there are so many cells. Okay, if you want to update a cell, it might take a lot of time. How do you do it? And also, see, all the cells here, you have wall line and bit line being connected. So when you put voltage on here, you are going to have current here, and put voltage here and current here, voltage here, current here. All the current will be accumulated. If all the current accumulated, you probably have some problems, scalability problem, because nothing is ideal. Okay, you cannot precise control the resistance value. Okay, so how do you control the error? Okay, how do you deploy and control all the modules? Okay, that will be a difficult issues. Then another idea we need to think about our application, that is graph computing or analysis. Okay, for graph computing analysis, well, we have to think about some massive, large networks such as large social networks. Okay, for social network, well, you have to think of a graph in irregular patterns. Okay, for social network, you know, some people have very good connection to many people. Some only have very few connections. Okay, so you don't have a regular pattern in your social network or some kind of messy network. Okay, then the problem is this: well, I have this kind of chips. How can I map them into these chips? Okay, well, think about it this way: you have a sparse graph. Okay, for the sparse graph, you have a lot of nodes. Okay, and you have some edge to connect nodes. And some nodes have a lot of connection. Some only have very few connection. Okay, it's irregular. And if you want to have a data structure to represent your graph, how can you do it? Well, that's an interesting issue. But how can you map the structure into your chips and do the computing? Okay, and find out the feature you like. That's a challenging point. Another one I want to talk about is content search. Okay, content search and matching has been used so frequently in different application domains, such as face recognition, recommendation. Okay, you want to do some matching for some data that's actually been requested by your users. Okay, and then when you want to do it, you have to have comparison. Okay, well, it's more or less like you have data here, and you want to search for something. You push the input inside, and you do parallel search at the same time and go out with the result. Okay, and see, oh, this is John. Okay, I know John, okay. Then he is permitted to come in, okay. Then the problem is this, how can you have the enough terrorism insertion and solve the power consumption problem, okay? And solve the space efficiency optimization because you have so much data. You probably have so many people to recognize. You have so many items in your recommendation system to recommend to your customers. How can you load your data inside? You probably have to think about a way to do it. Okay, so I don't have much time. Okay, I just want to show you one thing. Okay, well, for doing that over your memory chip, okay, you have to know your algorithm. You have to utilize your memory characteristics. If you do it right, you can do it fast and also, very costly to do it. Okay, but I'll give you some example. I won't go into detail. Anyway, consider the structure I just showed you. Okay, you have chips here. You have memory module here. You want to put your weight onto your program your or encode your weight onto your chips. Okay. The problem is, well, how do we encode it? Okay. Well, for different memory chips, they actually have a different way to program it. Okay. For example, if you have more time, you can have full set. Okay. So you program it at a higher voltage for longer time. But if you don't have time, you can program it with lower voltage and shorter time. But we are going to have more error. Okay. So I probably don't have time to go into detail. Okay. This paper we published 3 years ago with Professor Yanhao Zhang. Okay, that's actually in the top conference in embedded system. Okay, it shows that, well, if you can smartly utilize partial set, you can actually have the performance close to optimal case. Actually, maybe 3 or 4 times faster. Okay, in your machine learning and training. Okay, I probably cannot go into detail. Okay, too many slides. Okay, so let me jump to the final few slides. Okay, well, hopefully I have convinced you there are some scalability problems for von Neumann architecture. Okay, and for the von Neumann architecture, we have memory unit, we have storage, we have to fetch data, fetch instruction to your CPU, GPU, one by one. Okay, and the movement of the data between the storage or memory to the computing unit actually takes too much time. We cannot do it anymore. One way to do it is to combine CPU and memory and merge them together, become one unit. Okay, so it's more or less like your solid state drive that can compute, or you have memory that can compute. Okay, so you no longer move your data, you just compute. You have data there and then compute. It's more or less like your brain, right? For your brain, you have your input from your eyes or from ears, and you do training inside your brain. Of course, for human, we don't download our data, but maybe in the future we'll download our data and upload again. Okay, so we no longer use the way we do it for eyes and ears. Okay, but anyway, for certain application, you have to move data input and output outside your brain. Okay, but anyway, I don't go that far. But anyway, so I want to tell you that in the past 2 decades, we already see the new thing happening. I call it storage innovation. We have solid state drive. The new memory technology actually speed up our storage system. Okay, we go from millisecond to microsecond. We actually boost the system performance by 1,000 times because of new technology. But the new technology actually present us not just about the performance, but also behavior of your storage. So people keep doing that because people now work on the solid state drive, not just on your personal computer, but also in data center. Okay, and for the second part of my talk is actually about memory innovation. Okay, if you can boost the performance of your storage, that's very good. Okay, you actually improve your system performance a lot because you have a faster storage. But it doesn't solve the problem because your storage is still 1,000 times slower than your main memory because can compare microsecond, nanosecond. So can you can you reduce the gap between memory and storage? Or even, for example, you speed up your storage from microsecond again to nanosecond. That's one way to do it. The other way is bridge them together. That's what I show you in my first part of the talk. How if we combine them together? Okay. And if you do that, well, then you have to think about the design, new design of your operating system. If you do it successfully, you no longer need virtual memory because you have so huge memory. You swallow everything inside. You have your database inside your main memory. You have everything inside, okay? You don't do demand paging because they are in your memory. Why you do demand paging? Okay, so design will be totally different, okay? Then the second part of my talk is about in-memory computing, okay? If we do it that way, then we merge memory unit and computing unit. Memory is computing, computing is memory. We no longer need any data movement. Then, well, we can run deep learning naturally on those chips, okay? It's no longer simulation, what we see today, okay? So in that way, you can actually optimize your entire system design. You can have faster machine with very low energy consumption. Well, this is my final slide, okay? We'll be moving from CPU-centric design to the new world, okay? For computer, CPU is no longer the center of the universe. The center of gravity of universe already shifted, okay? Before we go to data. When you go to data, then you have to think about memory-centric or data-centric design. Otherwise, you are not going to scale up your application and your algorithm for the future application. Yeah, thank you very much. I took too much time for the presentation. Sorry about that, okay? I don't know I have time to take a few questions, okay?
I think we do.
Okay, thank you.
Okay, thanks for this very insightful keynote from Professor Ko. Okay, we have about like 5 to 10 minutes time for QA, open for the audience in the room and also for the online attendee. So I think we can start from the people in this room. Any question?
Thank you for the great talk. I'm Tei-Wei from National Taiwan University. So I wonder if you see any challenges in computing in parallel or in memory computing. For example, do you think in operating system we usually have locks, right? Do you think that would break if we do in-memory computing? Or do you see any new technology we might need for protecting concurrent processes to either in-memory for the faster storage device that we can do in-memory computing?
Okay. Thank you. Okay. That's a very good question. Okay. See, the current status we have today is the machine we have. Okay. And we have the entire ecosystem. You cannot rebuild the entire ecosystem overnight. Okay. You have storage, you have vendor that produce storage, you have vendor that produce CPU chips and GPU. Okay. People are not going to throw away because you have nice idea. You will not have that. Okay. So that's why people have to think about, well, how to go from here to there. Okay. That's usually what people think. Okay. Well, that's why even though there are some good ideas here, you can run your deep learning algorithm naturally on your new machine, but people probably won't buy it overnight. Okay. So you have to think about the path from here to the future. Okay. So that's why I say it's a very good question. Okay. That's why people will keep investing their money on storage because that's the entire ecosystem. But we all know that cannot solve our problem. Okay. Because data being accumulated at so fast pace. Okay. So people start to think about, oh, okay, for the storage, well, it's faster. Then can we make it even faster? Then can we make it smarter? For example, we put some FPGA, we put some computing unit into your storage. It becomes smart storage. Okay. so that you further reduce the data needed to be moved to the host. Okay, so different approach has been given. Okay, so make the storage faster, make storage smarter. That's a way to people do it for storage part. They call it near storage or in storage computing. Okay, and for the memory part, similarly. Okay, people will think about, well, if we want to totally erase or eliminate data I/O movement, how can you eliminate all the data movement? Well, people think about, well, how can we create huge memory with different hybrid memory architecture? How can we better utilize the memory even on another machine? Okay, there are many interesting, architecture design. For example, some of the work done by Professor Hong Xihao. He also doing some. People try to solve it. In architectural way to do it. Okay, and even for the in storage, computing innovation. Okay, people might think about this. Well, at the same time, Google is doing their TPU, and people are trying to create new chips for certain application. And put it this way, even though people will not create a totally new machine with in-memory computing, they probably build some accelerator like GPU, okay, that actually adopt the in-memory computing. It becomes the chips, okay, that just do computing, for example, face recognition, okay. So for in-memory computing, they probably will appear first as accelerator for certain computing, okay. They probably appear as certain control chip, for example, control your elevator, okay, control certain movement of your body, okay, because you don't need to build a so powerful chip to recognize a bird. You can build a very small chip that just do some reaction control of your muscle, okay. They can do it. So a huge diversity in the design. So anyway, so people actually, yes, they will have different design in different components, but we all know that might be the goal in the future, okay? But it take years to go, okay? But people have to survive on the way, right? They have to make money, okay? So they have to think about ecosystem.
Okay, thank you. And we also have a question from an online attendee, Song Jiang. Let me read the question. Okay, the question is, your proposed design need to understand or track data access patterns, including spatial and temporal locality. Is the tracking operation affordable, especially when NVM can be much faster than disk?
Well, interesting. That's an interesting idea. Okay, I think it's about the first part of the presentation. Okay, well, for the idea to be feasible, that's a very good question. Okay, think about the prefetching and think about the design. For example, prefetching for storage. You can actually have complicated algorithm for prefetching when you are dealing with storage, because the performance, the latency of storage is like millisecond or microsecond. It's so slow, right? For 1 microsecond, you do a lot of things on your CPU. Okay. So, but then for your memory access or smart memory access, you have to think about it in this way. Okay, they need to be very fast. Otherwise, the algorithm will be useless. Okay. For that, you have to think about how to control it in a very coarse granularity. Okay. Only do things at the right time. Okay. And also don't do many things. Okay. Otherwise, it will not work. Okay. So when you are, so for example, what I just showed you for the marking, page marking, you only do it when you store. When you store, they actually go down to the scale of microsecond. Then you have time. You quickly do analysis. And at the same time, you send the CPU to another process. You don't wait. Okay. Then use the overlapping of the next process execution and your analysis, and you do page marking. Then in that way, you don't actually waste your CPU time. Don't slow down your CPU. Okay. And do the analysis, you do it at very coarse granularity. That's why we invent the POP structure. You just control range. You don't do detail. Otherwise, you don't have time. I hope that solved the problem. I mean, answering about the question.
Okay, so any other question? Okay, Dan. Yes.
Yeah, Tony, good to see you again.
Good to see. Thank you for the great research and sharing with us. But from your research, and I just want to know, according to your vision, how long do you think it will take for people to start buying this idea?
Okay, it's good idea. Okay. Well, I think for in-memory computing, that's my imagination. Within few years. I would say few. Why? Okay, because I think many people are inventing their algorithm and chip design for certain application. For example, face recognition. Okay, and for certain control, they can have this kind of very simple neural network algorithm on a very small chips. That will be very cheap. Okay, but if you want to build a very powerful in-memory computing chips, it takes longer time. Okay, but for certain simple application, I think if there's a market, they actually can produce it in few years, 1-2 years, they can do it. Okay, as long as they have the market, because the technology is almost ready. People are trying different memory module. Okay, not just PCM, but also RAM, IEEE, and also even NAND flash. So that's what I understand.
That's another question. Talk about deep learning application and machine learning, mobile application in other area.
Oh, okay, good. Okay.
We probably need to repeat the question for online audience.
Okay. The question is, I talk about deep learning algorithms. Okay. How about other application for in-memory computing? Okay. There are many applications. For example, let me go back to one of my slides. Okay. One of my slides is about CAM and TCAM for content searching and matching. Okay. For content matching and searching, that actually happen in many applications. For example, routing. For network routing, when you have package, you quickly look at the package and look at the routing table and decide where to go for the packet. Okay. So for that kind of application, they already can use this kind of application. For face recognition, also the same. But for face recognition, especially for certain application with, not so many people, okay, then they can do it. I don't think the time to the market will be very far away, because if you consider millions of people, yes, it's more difficult. But for an institute like this, only tens of thousands of people, okay. Even for a small company, only a few hundred, very easy, okay. They can do it and put it on a very small chip and do pattern searching, content searching, okay.
I think we can, okay, the last question.
Thanks for this school. I'm very interested about your talk. I wonder if you could talk more about how to do error correction for in-memory computing, because it seems quite different from how to do for flash memory or something like that.
Yeah, thank you. That's a good question. Okay. For in-memory computing, since we want to have billions or millions of cells operating on a single chip, okay. So consider them that all the cells are being organized in a chessboard-like fashion. We have wall line and bit line, okay, connect them together. Then problem is when you have voltage on the wall line, all the data, all the current will flow through the cells and being accumulated on a bit line. When you have a lot of bit line, you are going to have some kind of uncertainty, okay, because there are some distribution. Because every cell is not ideal. When you have data going through and you have current, they actually have a distribution. Okay. And this is the highest probability, this is the lowest probability. But actually they have a shape. Okay. Like bell shape. Okay. More cell being, and you have more cell being connected on the bit line. You are going to have, you have more uncertainty on the data. How can you do it? Well, there are several ways to do it. Okay. For example, you can use redundancy to do it. Okay. Because they are probability. Okay. You can have multiple bit line to represent one bit line. So they are all distribution, right? So you can use them to collect an error, for example. And secondly, when you are doing computing for certain sensitive data, you can actually activate the chips. For all line and put in several groups, activate different group at different time. So you reduce the total number of cells that can accumulate their current on the same bit line. So there are several ways you can do it. You use algorithm to control the chips. Okay. You partition them or use redundancy to do that. Okay. Yes, so there are several ways to do it. Okay. It's different from what we do for storage. For storage, you do encoding, PCH, right? So that's different way. Yes.
Okay, I'm very sorry that I have to close the section because I'm running out of time. Please join me to thank Professor Guo for his insightful speech.
Thank you. Thank you.